In the first clip of this module, I quickly refactored the application to illustrate the benefits of asynchronous programming. I'm now going to undo all of that and step by step take you through the process of introducing your first asynchronous code. We're back working with a legacy web client. We certainly want to get rid of this, mainly because it's executing the web call synchronously. It's blocking the application from doing other work while it's downloading the data. To make this method run asynchronously, a very common misconception is to simply add the async keyword. The keyword async is added right before the return type in the method signature. You might now think that the code inside this method will run asynchronously. Let's run the application and see if this had an impact on the performance. When you search for a fake stock price, it still locks up. According to the operating system, it's not responding. After a little while, the application becomes responsive again. This is because the data has now been received by the application and the synchronous operation is completed. Let's jump into the code and talk about why this is still not an asynchronous operation. We can see that Visual Studio provides a hint that tells you that this method is marked as async, but the method doesn't use the await keyword. Whenever you encounter the async keyword, you must have the await keyword inside the same method. Async is a prerequisite for the method to be capable of being asynchronous. But simply adding it isn't enough. Remember this because it's extremely important. To make it asynchronous, we must replace this synchronous web call with an asynchronous alternative. We'd like to use the HTTP client instead, as this is a newer and better alternative. It will provide methods to asynchronously interact with web resources. This means that we could download data without locking up the application. Asynchronous patterns and principles are not only for communicating with web resources. Asynchronous principles are suitable for any type of I/O operations. In this case, we interact with a web API. But asynchronous programming is also good for reading and writing from disk, memory, or things like database operations. Then what about CPU-bound operations? For that, you'd use parallel programming, which is a way to divide a problem into smaller pieces that are all solved independently, while making use of as much computer power as possible. While an asynchronous operation do occur in parallel, the distinct difference is that with an asynchronous operation, you subscribe to when that operation completes. The task parallel library allows for both asynchronous as well as parallel programming. And you can even combine these principles. All right, back to the code. To fetch data from the web API and do so asynchronously, we are using the getAsync method on the HTTP client. I'm hosting an API in the cloud, which you can use throughout this course. The URL for this API is already added to the exercise files. So what makes this call asynchronous? GetAsync returns a task of an HTTP response message. The HTTP response message is simply the result this operation produces. A task represents an asynchronous operation. The variable response task is a task, and therefore a reference to the ongoing asynchronous operation. I bet you're wondering how to get the result produced by an asynchronous operation. If we explore the properties available on this task, you can see that there's one called result. Using this is often the first thing that people try, and this is a really bad idea. What happens when you request the result using this property is that it will block the thread until the result is available. This means that it will run the code synchronously. Given that, you probably understand why this is a bad idea. Instead of calling response_task.result, how do we get the HTTP response message? Then only proceed executing the rest of the method when that operation has completed. This is where we introduce the await keyword. Await is a way to indicate that we want to get the result from the asynchronous operation once the data is available. And most important of all, without blocking the current thread. As you see, adding the await gives you the HTTP response message. This value will be available as soon as the web request has completed. Then, to get the content of the web request, you have to read that once the response is received. There's a method called readAsString_async on the HTTP response message. This is also an asynchronous operation. If you call readAsString_async and then use the result property, this would block and make the code run synchronously. A word of warning here, calling the result property or even the wait method could potentially deadlock the application. Avoid using them if you can. This code retrieves the HTTP response message from the getAsync operation and puts that into the response variable. The variable will be set once the response is available. Only once that operation is completed, the next line will be executed. All of this without blocking the UI thread. Whenever you use the await keyword, the variable that we have on the left-hand side will always contain the result of the asynchronous operation. The API returns a JSON response, so before running the application, make sure that this is deserialized into an object that we can use. The list of stock prices can now be added to the data grid in the application. It's time to run the application, and this should now perform a lot better than it did earlier. If you set a breakpoint in the method, then run the application with the debugger attached, you can follow the way that this executes the code. When you reach the await, the control will be returned to the UI thread, and the user can continue working in the application. Once the asynchronous operation has completed, the next line after the await will continue to execute. The asynchronous principles that we've applied in this application is really not only meant for Windows applications or other types of UI applications. We can also apply the same principles on the server-side code in ASP.NET. Go ahead and open the ASP.NET web project inside the solution. Go to the file Home Controller inside this web project, and then find the index action. We can paste the same code that we had in the Windows application, which retrieves the fake stock information. Let's hard-code a stock identifier to make it a little bit more simple. To make it compile, we must change the method signature of this action to async task of action result. Because the method uses the await keyword, therefore we must also have an async keyword present. The fact that this returns a task of action result means that ASP.NET will have a reference to the ongoing asynchronous operation. And when the result is available, it can continue executing to get the action result from the action. Whenever you have a task, you pretty much always want to await that in the same method, mainly because it will give you the result of the asynchronous operation, but it will also make sure that the call was completed successfully and that there were no exceptions. We'll return the deserialized list of stock prices to the view, which will then be processed. And finally, the client that called this ASP.NET website will get a result. Running this gives an interesting result. Using async and await in ASP.NET does not make the client asynchronous. It might seem like it's a little bit different from how it worked in the Windows application. It took a little while to load the stock data, and you did notice that it wasn't, in fact, an asynchronous operation from the client's point of view. Then, what's the point of using async and await on the server? The big benefit of using async and await inside ASP.NET is to relieve the web server from work. The web server can then go ahead and work with other requests as data is being loaded from disk, the database, memory, or from another API. So far, we've looked at communicating with a web resource. But as previously mentioned, these asynchronous principles are appropriate for other types of operations as well. Head over to the class library in this solution which has a bit of pre-built functionality. There's a class here called DataStore, which uses a local file for the stock price lookup, instead of querying the web resource. You could consider this being an offline cache. Inside the DataStore, there's a method called getStockPrices. The method signature for getStockPrices indicate that this is an asynchronous method. We can determine this by seeing that it returns a task of t. It also uses the async keyword, which means that somewhere in this method, there's an asynchronous call, which this method expects a result from. The purpose of this method is to interact with the file system in an asynchronous manner. Inspecting this further, we can see that it opens a stream to a file on disk and asynchronously requests each line in that file. If you want to consume this method, you'd use it very much like you did with the HTTP client. Head back to mainwindow.saml.cs, remove all the usage of the HTTP client, and add a new instance of the DataStore class. To query for a particular stock, call the method getStockPrices. This returns a task of a list of stock prices. And you should now know that to get the result from this asynchronous operation, you use the await keyword. Once the stock prices have been loaded from disk, you'll get the result, and it can be added to the data grid. Run the application to make sure that it still behaves the same. Since all the data is available locally, it probably won't take much time to load the stocks, given the file isn't too large. You've now successfully introduced the async and await keywords in a C# application. You saw that the asynchronous principles are powerful no matter if you're working in ASP.NET, in Windows, or other types of C# and .NET applications. While this is a good starting point, there's still a lot to discover. Adding these keywords might seem simple and trivial, but we have only scratched the surface.